Okay, so we're going to go through problem 8, which is a great problem because it takes you through basically all of the different ways that we've learned to solve vector problems in one problem. And so if you read through it, we have Peter, who has lost his calculator, and he travels 11 miles at a bearing of north 59 degrees west. From there he turns and he travels another 26 miles at a bearing of south 33 degrees east. So he's traveling quite a distance here, looking for his calculator. That math lab is really far away. And so the first thing that we're going to do is we're going to set up a vector diagram. Okay, so we've got our little compass heading, and now we need to show that we're going 59 degrees from the north towards the west. So I don't want to go, too close to the middle. That's more like 45. Too close to west would be more like 80, so maybe about there. So I'm showing that that angle between the north and the west is about close to 60, right? And I'm going to travel 11 miles and then turn around and go 26 miles. So I don't want this one to be too long because my next one has to be at least double. You also don't want it too short, right? Because then your diagram will be too small for you to work with. So we're going to label a bunch in here. So we need our angle measure, 59 degrees from the north towards the west. We have our length, our magnitude, 11 miles. And this is a vector, so it needs a direction. It needs the arrow. Next, we're going to draw a new compass heading at the head end because that's where we're going to begin our next vector after he turns. So go ahead and draw in your next compass heading. Okay, now that we have our next compass heading in, let's remember what we know about parallel lines. Our north-south lines are all parallel to each other, and we're cutting those parallel lines by our transversal, our vector here. And so if we have this angle of 59 degrees, that's going to have a congruent angle over here, also 59 degrees. So when we're drawing our south towards the east, 33 degrees, that's going to be about half of this 59 degree angle. Slightly more than half. Okay, so maybe about there from the south towards the east. Now, the length of this is 26, as I said earlier. That's more than double the length of the last one. So that's maybe about the same length. I want to go about double, a little bit more, to make this a little bit more realistic. Okay, now we can see that this is crossing back over that north-south line that I had drawn in before, and I'll include my little arrow. And so you might be wondering, well, how do you know for sure where it's going to end up? And the answer is right now we don't know for sure, but after we find our horizontal and vertical components, we're going to be able to adjust our diagram if we have to. So for now, let's just go ahead and label all of this. So remember the angle here, just to this vector, is 33 degrees from the south to the east. The magnitude of this vector is 26 miles. Okay, and so now it's talking about, all right, draw this realistic diagram and find the net distance. The net distance just means the overall, so basically the resultant. Okay, so let's draw that in from his start to his end. And I like to differentiate, as you know. Okay, but don't forget the direction. Okay, so here's our resultant vector, r, with its direction, starting here and ending here. Okay, so for part A, it's asking us to find that net distance as a sum of horizontal and vertical components. So if we start to do this, our first vector is 11 miles. Times cosine of its angle, but we can't use 59 degrees. So I'm just going to leave that blank for now. Okay, now that's our horizontal component, plus 11 sine, whatever the angle that we're going to use will be, times j. And we're going to add in our 26 as well. So let's go ahead and do that. Okay, so when we're using our horizontal and vertical components, we have to use our standard position angle, theta. We can't use a bearing measure. And so if we're looking at our first vector that we drew here, the 11 miles at 59 degrees, if I just draw that vector off to the side, I don't want to get in the way of the rest of the diagram. Here's 59 degrees. Well, its standard position has to start from the positive x-axis. There's its theta. Okay, so its theta is really going to be 90 plus 59. Or 149 degrees. Okay, so that's the angle that we can use with this because that's our standard position angle that's going to give us the information we need. Okay, so next let's find the standard position angle for our 26-mile long vector. And so again, I'm going to draw a little picture of that off to the side just so that I have that separate from my diagram. So it came from this compass heading and it went kind of like that. Now this measure was 33 degrees. So if we're looking for the standard position angle from the positive x-axis, okay, this theta traveled 270 plus the extra. So in this case, we're going to use 303 degrees. Okay, now we're ready to calculate our horizontal and vertical components. And if you remember, we can calculate the horizontal parts by themselves and the vertical parts by themselves. So let's calculate just the horizontal parts. And it really does save a little time if you can do this all at once. So on your calculator, you're going to type in 11 cosine, all right, it's a little bit dim, 11 cosine 149, close that off, and then plus 26 cosine 303. Okay, don't forget to store your value. And you can round to the nearest hundredth when you write it. Okay, so we get a magnitude or a horizontal distance of 4.73. Okay, we're going to do the same thing for our vertical. And you can either recall the last thing entered. This one, it's not that much to type it in. Just make sure that you're changing your cosines to sine. Okay, don't forget to store your value. And you can either say plus the negative or just minus 16.14 times j for the vertical. Okay, so that's our answer for part A. But let's take a look at the meaning of that answer. Okay, so we're looking at our resultant vector r over here. And so that resultant vector, and I'm actually going to change it from being dashed since it's a different color, has its own little right triangle, right? And so its own little right triangle, according to this, we have a horizontal distance of positive 4. So here's positive. Okay, and that's our 4.73. And then it has a negative distance of 16. So remember how I mentioned that once we do these horizontal and vertical components, one of the nice things is that they'll help us verify that our diagrams are correct. And in this case, it verified that the way that I drew this was in fact correct. Okay, so if I hadn't drawn my 26 miles long enough, I would have ended up over here in quadrant 3. And in quadrant 3, my A value should have also been negative. Because my A is positive and my B is negative, I know I have to go to the right and then down, so I have to be in quadrant 4 for that resultant vector. So that's great news. I didn't have to fix my diagram. If you notice that yours is a little bit wrong, then you do have to fix your diagram. Because in the next part, we're looking for rewriting our resultant vector using a magnitude and a bearing. So we need to be sure where our bearing measure is going to be measured. Okay, so let's move on to part B. And we're going to do just that. So the magnitude over our resultant vector, once you have these two, and we're not allowed to use the law of cosines yet, but once we have these two measurements, well, we can use the Pythagorean theorem, and then we can use tangent for the degree measure. So go ahead and calculate out your magnitude and also the initial principal value that your calculator gives you. Okay, so like I said, for the magnitude, we're going to use the Pythagorean theorem, and we have our two values in here stored in our calculator. So let's use those. So I'm writing on the paper the decimal approximations, but in my calculator, I'm not typing those in. So I get a magnitude of 16.8 approximately, 2, rounding to the nearest hundredths. And remember that this is a distance, and we were given miles to begin with. Okay, now our angle isn't quite as straightforward, but we can come up with the principal value in the calculator. And so we'll do second tan, and then again, use your stored values. So this time it's b over a. And remember, for tangent, it's always going to be b over a. So we get this principal value of negative 73.66 degrees. But that's not the bearing that we're going to be using. Okay, so let's look on our diagram where that is. Remember, this is from this right triangle that we drew with the resultant as the hypotenuse. So this theta measure, the negative 73, is this angle here. What we need is the bearing for that resultant vector, and of course it's always measured at the tail. So what we really need is this outside angle. Okay, well, the bearing and the theta that we just found, right, those have to add up to 90 degrees. So to find the bearing, we're going to say 90 minus 73.66. But in our calculator, remember that this is already negative. So in the calculator, I'm just going to say plus 90. Okay, so my bearing, the degree part, is 16.34 degrees. And then I'm going from the south towards the east. So you start with your north and south, and you end with the direction you're traveling in. So for part B, we are traveling 16.82 miles at a bearing of south 16.34 degrees east. Now the last part of this top part of the problem says find the bearing of the return trip back home. Okay, and so remember, for the return bearing, you don't have to recalculate. We're going to use 16.34 degrees. The return bearing will involve 16.34, but it's the exact opposite. We're now at this head end of our bearing vector, traveling backwards. Okay, so remember, our north-south is always going to be parallel to each other, and so our bearing measure inside here will be congruent to this alternate interior angle, which is exactly what we're looking for. It's measured from the north-south towards there, so that's going to be your bearing 2. Okay, so our return bearing is going from the north towards the west. Okay, so we were able to find all of the information about this resultant vector just using our horizontal and vertical components. In part D, it says basically to redo the problem. This time we can't use any of the horizontal and vertical component information that we did earlier. But now we're allowed to use the law of cosines. You don't have to redraw the diagram. If it's helpful, go for it. Remember that when we're trying to use the law of cosines, we can always find, just using the geometry of the problem, we can always find the angle that's opposite our resultant. So in this case, the angle opposite the resultant is this interior measure. Our 59 degrees out here is congruent to the alternate interior angle that's formed with our parallel north-south lines and our 11-mile vector. So that's this one. Okay, so that is 59 degrees. So knowing that, knowing our outside is 33 degrees, so we can just subtract 59 minus 33 and come up with 26 degrees for our angle alpha. Okay, so once you have that angle measure, we can use the law of cosines and we can calculate our magnitude of our resultant vector. So once you've written out your law of cosines to find the magnitude of the resultant vector r. Okay, so now that we have found the magnitude of our resultant vector and we've matched that up, now we need to find our bearing. And so remember that we're looking for the bearing in here. And so to find that, we're going to need the overall angle inside our triangle. So if you haven't yet done so, make sure that you store your recent value. And we're looking for this angle measure inside the triangle, the overall. The key here is remembering it is across from the 26 miles. So when we write out our formula for that, we're going to need to put minus 26 squared last. Okay, so we'll write out our formula. Of course, use your stored value in the calculation, even though I put 16.82 in the formula, I'm not going to actually type that into the calculator. That's our initial value. Remember, that's for this big obtuse angle across here. So remember, what we're looking for is this part of that whole angle. What we can do is we also know this little part of the angle. We can find this guy because that's going to be 90 minus 59 degrees. And so then we can subtract that off as well as that 90. So we can subtract that 90, this 90 minus 59 from our 137.34, and we're going to be left with our bearing. And as you can see on the calculator, we sure do. So we get that 16.34 degrees. And then remember that this is a bearing measure. It's going from the south towards the east. So we'll include that again. So we did, in fact, get the same results that we got from up here. And now we have used components to solve one problem. We also used the law of cosines, and we were able to do both ways.